Leslie got flu, so he can't be here today. So I will give you guys lecture today. Okay, so bad news, he won't come. So good news, don't worry about your attendance. Okay, I will talk the rest part of the thread. Okay, let's quickly review what the thread means. Thread is kind of a basic unit of CPU utilization. So what that means, if you create or run your program, so you will create a process first, but in the process there's a thread. So when you exactly your instructor in your process or in your program, CPU is using the basic unit is thread to run your instructor. So that is why we use thread. And also, one processor can have many threads. And this is the PCB block. What this thread information is part of the PCB. And we can see this one process which have three threads. What's their data structure like? And also thread can have their own stack pointer, register, and scheduling properties, and some of another like signals, also specific data. So these things you can't share with another thread. But if you in one process, you can see different threads can share one process data. So this is the difference. We'll see. This on the left side is a single thread process because it is one thread. The right side is a multi-threaded process. You can see these three threads are shared the same code, data, and files, but they have their own stack and their registers. Okay, benefits. So if you run several threads simultaneously, so if one dead or one is blocked, the other one will continue running. So it just improve the efficiency. Also, we can share the resources because we have limited memory. So it can save the resources. Also, its economy. The thread is 30 times faster creating compared to creating process. And also, when you're switching context, it's 5 times faster than process context switch. This is a table that shows when you create threads, it's more faster than creating process. Okay, in the first chapter, we know that computer have two models, user model and kernel models. So in threads, we also have two models, two types of threads. It's user thread and kernel thread. So as we all know, when we run a program, if we want to call the system call, we will have to convert the user mode to system to the kernel mode. So at this is the same. If you want to use kernel mode, you have to convert your user thread to the kernel thread. Also, on the user thread side, it will be managed by the user level thread library. It will in charge of creating, scheduling, managing threads. And also, there's one situation. If you connect to one, if you several threads can connect to just the one kernel thread, it will have some problem. We will talk about it later. If this kernel thread was blocked, so all the user threads will be blocked. So this process are blocked. And also the user threads are independent on OS is in charge of by the user thread library. So there are three primary thread libraries. Windows, Java, and P-threads. We will talk about the detail of P-threads. also there's a kernel thread. Kernel threads obviously was supported by kernel, and also supports creating, scheduling, and managing all the threads methods. And it needs, it will be slower. Why? Because when you want to use the kernel thread, you have to change the mode, so it takes time, so it will be slower than the user thread. So there's another situation here. So even if one thread is blocked, the other can be processed. So it's a little bit of contrast to the other one. So we will talk about this is another situation that is when you connect to from user to the kernel thread, we use a many-to-many connection ways, so we can solve that situation that even if one thread is blocked, the others can be processed. So the example of kernel threads, you'll see all the popular platform operating system have their own kernel threads. Okay, this is a multi-thread server architecture. You will see the server will running listening thread who want to receive the request from the client. So it will run like for a loop. It will run here. It's a loop. It's a listening thread. So if the server got the request from one client, he do two things: create a new thread to serve this request, and at the same time, this thread will back to the for loop to continue to check whether there's a client request or not. So this is kind of multi-thread. So before that, before we use the multi-thread, if we get the request of one client, we will create a process. So it will take more time, also waste of the memory. Because when you want to serve the request, or maybe the, in the process, most of part of the code is the same. So why won't we just save our memory? So we just create a thread that we can share the data. So this is the multi-thread server architecture.
Excuse me. So there are two threads acting at the same time.
Yeah.
So one for the listening the new request.
Yeah. The listening thread was all running, just get the request, and also it should, it can that maybe these two threads are listening to the request.
So for if two threads are listening, how many processes do we have?
It depends. You can decide how many threads you can handle. So it's also, you should check the ability of your computer or server. So because when you, because it would use the resources of the computer, so you have to limit the resources. So even if you have two threads, so it means when the third clients want to request the server, it has to be wait.
So no, technically because if there's only one processor, it's only one thread can run at a time, right? So is it like changing between
Yeah.
for two
At first time, it will be one process, but it also depends on the request. If the request is so many, we will create another process. So the benefit is the same. You can reduce the response time. Also can share the data. And also this have scalability. Because if we have a multi-core or multi-processor, we can create different threads, or when so many threads on multi-core. Okay, when we want to make a program running on the multi-core, we will face these 5 challenges. First is dividing activities. So give me an example. So if this is my code, I divide this part as an activity, this part as an activity. So we'd rather to divide the activity, make them independent. So why we want to make it independent? So if this thread use the data, is in this thread. So what happened? If the thread is running in the middle, you have to wait this thread. So it doesn't make sense because if we want to use multi-thread, we want to run the threads simultaneously. So if we have to wait this another thread, so it will take a longer time. So why would this make this one thread? So we will consider about carefully when we divide the activities because we don't want the thread will interrupt or influence the other activities or other thread. Also, balance is the same. If we want to you create different threads, one thread is use 10% of the CPU, another is using the 90% of the CPU. So it doesn't get the whole benefit of the multi-thread. Data splitting and data dependency is kind of the same because when you want to share maybe one data, maybe now one thread is changing this data to one, but this thread wants to use it, but you want to check whether if this thread is run after this thread, but this thread, the data can it's like we use this share this data. So we want this thread use this thread want to use this data after this thread, but this thread is changing. So we don't know we want this thread or not because if I want to, this thread wants this data to be 0, but this changed to 1, so it doesn't make any sense. So testing and debugging is the same. It's a little tougher to test in multi-thread because it's hard for you to find some problem or the syntax error or something, or logical error. So the main purpose of the multi-core program is to make your program can run parallelism and concurrency. But this two conception is different. We will see the details. This is a comparison between the concurrency and the parallelism. You can see parallelism is means at the same time you can do two things. It's like when I speak, I can move my hand. It's in the same time slot. I can do two things. But concurrency means that in one fixed time or during one time slot, multiple threads are making progress. So you can see, for example, if I divide this time slot to this one, you will see the thread 1 and thread 2 are both running. And if they just only you want to use only one time slot, you will get the result. But if I divide this one, you will see I just got the thread 1's result. But if I increase the time slot, if you do 2, I will find that I got 2 results respectively from the thread 1 and thread 2. But if you want to see this concurrency happen, you will have to take a long time. So you will see the two threads are making progress. So it's the same. So it is that it is possible that concurrency without parallelism. It's kind of the current concurrency model is kind of single core because you divide the time to different time slots. Each time slot you can just run one thread. So if you look it into 1 minute or 2 minutes, it seems like it's doing the parallelism, but it's technically not. So the type of parallelism, these two types, data parallelism and task parallelism. Data parallelism is same. It's like if I want to get the result of the summation of 1 to 100, for example. So data parallelism is like this thread counts the summary from 1 to 50. The other thread counts 51 to 100, so it's called data parallelism. The task parallelism is very simple. It's like when I browse the internet, the other thread is printing the pages, so it's task parallelism. Okay, how we can measure the benefits we get from the thread? So this is the logs. So we will see if kind of different view conception. S is the serial portion, and N means the processing cores. S is the serial portion. So what means the serial portion? So it means if you use if you write a code, so this part may be in one thread. So this means this is not serial. It means this part of code can be parallelized. So it should be some part of your code that when you run your code is serial, it's sequence coded like one by one. So in this equation, you will see the speed up have limitation of this part. So we can calculate it. If your program, the serial partial of your program is 25%, and the parallel part is 75%. Compared to using one core, if I using two cores, I can get 1.6 times faster than using one core. So there's another ideal situation if we have unlimited resources, if we have unlimited infinity process. So you will see this part will limit to 0. So this speed up will smaller than will approach the record of the S. So we can make a example if we still my code is the serial part of my code is 25%. You will see we just get 4 times faster. So it doesn't mean more cores you have, the more speed up you can have. So it has limitation. And this is the user thread and the kernel threads. And user threads is managed by their user level thread library. So operating system can handle that, and the kernel thread was in charge of the operating system. Okay, there's 3 different models between these 2 modes connection. One is many to one. So the user will have so many threads. They are just to connect to one kernel thread. So obviously we can see the problem we will have if this kernel thread was blocked. All the user threads use this connect to this kernel thread will be blocked. So we can get benefit of this when using the multi-thread program. So there's a few systems are using this model. So another type is one-to-one. One-to-one is one each user level thread will maps to another kernel thread. So it will solve the problem that when the kernel one kernel thread was blocked, the other user was blocked all over. So, but still they have problem because the kernel thread also have limitation. You don't want to create huge amounts of user thread to connect to kernel thread because kernel thread also have limitation resources. Kernel thread have to maintain the system running. So the kernel have to keep or resume part of this their kernel thread to make the computer running. So at the later we'll talk about the thread pool that can limit the user to create the user thread. You will see the number of threads per process sometimes are restricted due to the overhead, because it doesn't mean more thread you have have the one benefit, because the kernel thread have to handle all the system calls. If the user just get the whole resource of kernel, so the system can't respond. So it's sometimes it will the screen. If sometimes you are running a lot of programs, the screen will be freezing. The third mode is many-to-many. So obvious, so user thread can manage many kernel threads. Also, we call this as two-level mode, and the example is 4. In two-level model, the system can handle whether the user thread is very important or not. So whether if the user thread is important, so it will connect to the kernel thread in the model of 1-to-1. So if it's not important, it will connect to the kernel thread many-to-many. Thread libraries provide a programmable API for the creating the malicious threads. So in the user threads, the library ties in the user space, and in the kernel side, the kernel levels library was supported by the operating system. Okay, let's talk about the pthread. Pthread is provided either as user level and kernel level. So both sides we can use pthread. So, but most of the case, the operating system are using pthread. So pthread is based on the POSIX standard API. So it also is an API level. So it's a kind of a standard guidelines. So it's a specification, not implementation. So if you want to create your own kernel threads library or something, the developer can implement on their own laptop, own operating system. So API give you the different behavior you can do. So you can implement it by yourself. So we will see different platforms use pthread. They use the pthread as an API. So they maybe use different rules, different syntax to in their system to maintain or control the threads. And this is an example of pthread in C, I think. See, in the main, we create pthread ID, and each pthread have their attributes. So we get the ID and attribute. Because each thread have to be have their attribute. So at here, we create the pthread, and this parameter is the pthread ID and the attribute. Also, which method you want to use, and pass the parameter to this method. And this runner method is here. You will see it's the summation of from 0 to from 1 to the given number. Also, there's data. There's a global data, so we can share. The main, also the runner can share this data. So this is an example example of creating the C thread. Also at this situation, main function is also the parent thread. So you will see this. So in P thread, there's a synchronization problem. It's like if you want to create a child P thread, the parent thread will have to wait the child thread to be done. And after that, the child thread will give the parent thread a signal. So we will call this method called join. We give the child thread ID, then tell the parent thread that I'm done, I'm ready. So the main thread can continue running their program. This is C in Windows. You will see the architecture is the same, but different syntax. There's also a summation function, and there's create a thread ID. Here we use a thread handle to handle the synchronized problem. You will see here we create a thread with this parameter, this summation function, thread function, and there's a return identifier. And also here we will check whether this thread is finished or not. So if it's finished, if it's not finished, we'll wait for the signal. So it's finished, we'll call this close handle. So this whole thread will be terminated. Java, I think most of you guys are very familiar with Java threads. There are two ways you can create a thread class. Also, you can implement it with a runnable interface. So it's here the same. Different is in this example, it creates a subclass to get the summation of the result. You're seeing here, it's create a new thread and thread start. And if after the thread started, you will find the runnable method here, and this is a run method. And after that, you're going to see there's also a join method where we call it to get whether the child thread is finished or not. So we are using thread all the time, but we can't, see it because it's too complicated. So we just hide it in the program level, also in some compiler and runtime libraries rather than programs. We have three methods. You can explore them. One is thread pools. I just mentioned that. Why we want to create a thread pools? Because when you want to create a thread, it will take time. Even if it's faster than creating a process, but it will take time. So when we create a process, at the same time, we will create a thread pools that wait for the thread to be filled in. So it will reduce the creating time for sure, even if it's very small. Also, it can allow you to the number of thread in the application. I just said the kernel thread have their limitation. If we just want to, this process have four kernel threads to connect with the user thread. So I just create four user threads size of the threads pool. So if there's a 5 threads want to connect to the kernel thread, you have to wait till one of the 4 has terminated. Another one is OpenMP. It's a set of compiler, directive, and API for C or C++. So it provides identifiers, it's like arrow regions. So if you in the program you see this kind of phrase, you know, after this phrase, this part will be thread, multi-thread function. So it makes it visible. The other one is semantical dispatch. It's used in Apple OS. Also, it allows identification of parallel sections. It's like the OpenMP. Also, using thread have some issues. It's like first is semantic or fork and the exec. So as we all know, when you want to fork a process, it will copy the parent process, and when you run the exec, it will upload the child program. So sometimes I just want to copy the one thread that just want to just one thread want to copy. So some Unix system have 2 versions of fork. So if you one thread or one process called fork, it just copy the threads that invoke this fork. Or the another way is just to copy all the process, all the threads from the parent process or thread. Signal is kind of event. So when the system makes some event, it will give you signal to some process or thread. So for example, in your program, if you make some illegal data access, or like some variable divided by 0, it will cause a signal. So it will be generated, like the slide said, will be generated by a particular event. So this is the event. The operating system can allow you to one number to divide it by 0. So the signal is delivered to the process which want to handle it. So there are 2 signal handlers. Defaultly, the signal will deliver to the kernel thread or kernel process. So if here I divided a number with 0, so the kernel thread will close or terminate this thread or terminate this process. Also, user can define their own signal handler, so you can add your own function. You can override your default signal handler. So there's different ways to deliver the signal to multi-thread. So deliver the signal to thread which the signal applies. Just maybe one example is that if you want to read the data from the hard disk drive, so you have to wait. Maybe there's I/O wait, or maybe the CPU is running another thread. So you ask the CPU to read the data from hard disk drive. So if the CPU get the data, so it will give the signal to the thread. So it's like deliver the signal to which the signal applies. Because this thread give the signal, because this thread want to retrieve the data. So now I get data, so I back to you. Another way is deliver the signal to every thread in the process, and deliver the signal to certain threads. Maybe part of the threads want to listen to the signal, or all parts of the signal. It's like if you create a program that wants to listen in the mouse event. So maybe a part of the like display part want to get signal. So we'll delay the signal to the display part. So it's like I click the mouse, this gives the signal, this is an event that deliver the signal to the display. So in the display, they will show different results. Also, we can assign a specific thread to receive all the signal from the process. So like the process termination thread also has their own cancellation way. And also like process, it can be terminated before they finish their job. Thread also maybe sometimes have to be finished before they finish their job. For example, if there are 4 threads are searching the data in one data set, so one thread gets result. So the other 3 threads will be terminated. So that's called thread cancellation. So thread to be cancelled is our target thread. There's a 2 approach. Is a asynchronous cancellation. So it means if I want to terminate, so it will terminate immediately. Another is deferred cancellation, allow the target thread to check the status what the programmer or the user give to the thread. It's like if I create a parent thread, I create this parent thread, create a child thread. So if I want to terminate the parent thread, I have to wait the child thread to be finished. So this kind of deferred cancellation. This kind of for loop, it will check every time whether the child thread is finished or not. So it's called deferred cancellation. In thread, there's another storage type, not storage type. In the thread, we say they have their own stacks registers. So in this way, the thread are also allowed to have their own copy of data. So it's kind of like a local variable. But it's not, because one thread maybe can use different method. So it means the thread in this field is kind of not local variable, because it can use through different functions. So it's a difference between local variable and the TLS. So but it's kind of way, but it's just in one thread is kind of like statics data, because all the function in this thread can use the data, but it's also different. But it's similar to static data, but it's different because each data in different threads where you can the function can use is unique to each thread. It means this thread it has like kind of static data, this kind of method can use, but to this another thread, this thread cannot use this data, this thread 1 data. And also the function in the thread 1 can use this thread 2 data. So for them it's unique. So there's a scheduler activation. So what that means, we talk about the two-level model as a user thread and kernel thread. So how we can allocate the different user thread to different kernel thread. So between them, we add an application called lightweight process to manage the or schedule the allocation of the threads. So the lightweight process have a virtual processor that can schedule the user thread to run. So if I have 5 user thread, I just have 4 kernel threads. So the virtual processor will manage which one go to the kernel thread, and there's one left to wait until another one of 4 is finished. And also each lightweight process will attach the kernel threads. And also there's a way that the kernel thread want to give feedback of the to the user thread. So if one kernel thread was blocked or was not responsive, so it will give up course to the lightweight process. So the lightweight process, the virtual process in the LWP will decide, okay, this thread, this kernel thread not work, so I put the user thread back and give this user thread another kernel thread which is available. If it's not, so I get back this user thread to user side and wait the other user thread finish, then put into the another available kernel thread. But at the same time, if the kernel thread, the block kernel thread is runnable now, so also the kernel side give up course to the LWP, so the virtual process will turn the former user thread which was running on this kernel thread resume their running. This is our operating system thread. So in Windows thread. You can implement one-to-one mapping at kernel level. So each thread contains ID, the address the set. And also a private data storage area used by runtime library. And also this dynamic link library. Okay, the primary data structure of the thread in Windows is pthread, kthread, and tb. So what it means, so the thread include the pointer to the processor to which thread belongs to the pthread. So this is the first thread we created. So after that, we will create a kernel thread block. So the thread have a pointer to the kernel thread block. So after that, it's kind of when we talk about the computer, when we reboot it, the first process is kernel. So after this 2 thread was created, it's kind of the system was boot. So after that, there's a thread environment block. It contains the thread ID, user model stack, and the thread local storage. And it is in user space. You will see the graph here. You will see it's kind of booting of the system from left side to right side. So we will create the each thread first. Then we'll onto the parallel process. Then we'll create the case thread and have a kernel space. And this left side is kernel space. So it's kind of we are booting the computer. This is a kernel mode, or this is a kernel process. So after that, based on the kernel thread, we can create our own user thread. So it's kind of can create our user mode or user process based on the kernel process. This is a Linux thread. So Linux first one task rather thread. Okay, they use different system cores. Okay, this is the end of this chapter. So I think next lecture, Professor Lee will back and continue the next chapter. So this is today.